It's now time to look at homomorphisms and isomorphisms. These are maps between different groups, and just like many other similar maps, they give us more of those interesting connections we're always on the lookout for. Then, to close the series on group theory, I will briefly touch on the theory of rings and fields. Our introduction to abstract algebra wouldn't be complete without at least mentioning them. And I also want to move towards the next series, the one about linear algebra, where we will talk about vector spaces. I already mentioned the word homomorphism in the video about monoids. Remember the example of string concatenation, where strings consist of blocks. This is a monoid, but not a group, because there is no such thing as a negative string. We also have a second monoid at the bottom, the natural numbers with addition. Again, this is not a group because it lacks additive inverses. We introduced a function that maps from one monoid to the other. Every string has a length. The length function maps strings to natural numbers, but it does so in a very clean and consistent way. Whenever you concatenate two strings, their lengths add up. So, the length function not only maps strings to numbers, it also turns concatenation into addition. It's very consistent. You can either concatenate first and then take the length of the resulting string, or you can take the lengths of the input strings first and then add those up. The result, the total length, will always be the same. That's the key to a homomorphism. It maintains all the relationships between the elements of the monoids. Formally, we write this property with an equation. This is the definition of a homomorphism F between two different monoids or groups. These funky symbols are just the two binary operators. The formula literally says, if you perform the binary operation in the first monoid and then map the outcome to the second one, you get the same result as if you first map to the target monoid and then perform the binary operation there. Now, you may have already realized that you can easily invert the length function. For any natural number n, you just map it to the unique string of that specific length. In this sense, you can look at the homomorphism from the other direction, bottom to top. Again, it perfectly preserves all relations. When a homomorphism can be inverted like this, we call it an isomorphism. So an isomorphism is just a homomorphism that works in both directions. When two monoids are isomorphic, they have the same number of elements and the same relations between those elements. I said that the length function is invertible, but obviously the strings and natural numbers in our monoids are still not invertible. So be careful, the invertibility of the morphism has nothing to do with the invertibility of the monoid elements. Also notice that the length function is invertible only because our strings are made from identical blocks. The colors of the blocks are just for clarity, so you can consider all blocks as the same. If the blocks had different letters on them, multiple strings would have the same length, and then we would no longer be able to get back from numbers to strings. In that case, the length function becomes merely a homomorphism, but no longer an isomorphism. What works for monoids also works for groups, because groups are a special kind of monoids. The idea is exactly the same. A good example is the exponential function. It's an isomorphism between two groups, the real numbers with addition and the positive real numbers with multiplication. I like this example because it shows that the rather abstract definition of a morphism is actually really familiar. It's identical to this well-known property of powers and exponentials, mapping from addition to multiplication. The inverse of the exponential function is the logarithm, which is only defined for the strictly positive reals. Since you can go both ways, this is not just a homomorphism but an isomorphism. We can draw this all out more explicitly in a diagram. We have two monoids or groups. Their sets of elements can be very different, such as strings versus numbers. And each also has its own binary operation, such as concatenation versus addition. Mathematicians often call both of these operations multiplication for simplicity. Now think of a morphism from the first monoid to the second as a kind of dictionary that translates between them. It maps strings to numbers, for example. For any such mapping, there are two different paths you could follow. You could first use the dictionary to map two given input objects over to the target monoid, and then multiply the mapped objects using the multiplication of the target monoid. This gives you a new object on the right. But you could also do this the other way around. You could first multiply the two given input objects directly in the original monoid on the left, and then map the result over to the right using our dictionary. For a random dictionary, this would result in some arbitrary object on the other side. But for a morphism, the resulting object is the same one that we found along the first path. When we state that we want the two results to be the same, we get the formal definition of a morphism. So now you see where this formula comes from. Graphically speaking, both paths lead to the same destination. The graph closes up at the end. This is very similar to how we closed the commuting diagram in the previous video. There is an entire domain of math called category theory that studies these morphisms and diagrams. It's very abstract and advanced, so we won't get into category theory here. For an isomorphism, we can invert the dictionary, allowing us to go back from the second monoid to the first. When two monoids or groups are isomorphic, you can usually consider them identical. They behave in exactly the same way. They have the same properties, the same relations between their elements, and even the same internal quotient structure. So, even though the rotations of the square and the addition modulo 4 are technically not the same, they are the same for all practical purposes. If you want to be precise, you would say that they are the same up to isomorphism. Why are morphisms useful? Basically because they allow us to study one monoid in terms of another. In the previous video, I showed an example of how you can transfer knowledge from one group to an isomorphic one. If you can easily prove that addition modulo n is abelian, then the rotations of a regular n-gon must be abelian too, because both are the same up to isomorphism. You can often perform a difficult operation by translating it to a different monoid where the operation becomes easier. The logarithm is again a really good example. It turns multiplication, which can be difficult, into addition, which is typically easier. Later, after we look at linear algebra, I will show a more advanced example. We will look for morphisms from arbitrary groups to groups of matrices. These mappings are called matrix representations. They allow us to study a group by doing linear algebra instead, which offers new insights into how the elements of the group interact with each other. Let's see if we can find some interesting morphisms between these two groups. On the left, we have the symmetries of the square. On the right, you see a tiny group with only two elements. If we call these elements 0 and 1, this is actually addition modulo 2. The table basically reminds us that an odd number plus an odd number always gives an even number. Or you can think of this as the exclusive OR operation in computer science. Anyway, we want to construct a few morphisms between these two groups. Since the target group has fewer elements than the 8 elements on the left, we won't be able to invert our mapping, so we will have to settle for a homomorphism. Okay, first things first. A morphism always maps the neutral element to the neutral element. That's because we want to preserve the group structure, and specifically we want to preserve the defining property of the neutral element. You can easily prove this using the definition of a homomorphism. So, whatever our morphism will look like, it will always have to map the 0-degree rotation to the number 0. Next, we have to decide what to do with the 90-degree rotation. We have two options. We can map it to 0 or to 1. Let's pick 1 for no specific reason. The key thing to remember is that the 90-degree rotation generates the other rotations. Once we decide where to map the generator, we no longer have a choice for the other rotations anymore. The 180-degree rotation, for example, must be mapped to 0, as mandated by the formulas on the screen. And in a similar way, the 270-degree rotation must be mapped to 1. As I mentioned earlier, once you know what happens to the generators of a group, you know what happens to all other elements as well. Next up are the reflections. As in an earlier video, let's use H as the second generator. Again, we can decide to map it to 0 or 1. But as soon as we make our decision, the mappings for all other reflections are fixed. If we decide to map H to 0, for instance, you can calculate the values for the other reflections. We have no more free choices to make, and so our homomorphism is ready. This is one possible strategy for finding morphisms. You select target elements for the generators, and then you calculate everything else. Okay, that's great, but there's more. Let's create another morphism. We will make some different choices this time, and this will lead to an interesting discovery at the end. As before, the neutral element must be mapped to 0. Let's also map the 90-degree rotation to 0 this time. This fixes the values for the other rotations. They all have to be mapped to 0. So far, this isn't very spectacular. In fact, if we decide to map H to 0 as well, then all the elements of our group will get mapped to the same element on the other side. This satisfies the definition of a homomorphism in a trivial but boring way. Instead, let's choose to map H to 1. Again, once we make this decision for our generator, the other reflections follow automatically. We end up with a situation in which all rotations get mapped to 0 and all reflections to 1. And here comes the surprise. Let me color the number 0 blue, together with all the elements that are mapped to 0. I will also give a red color to the number 1 and to all elements that are mapped to 1. In an earlier video, we used these colors to mark the orientation of the square. The rotations preserve the orientation, while the reflections flip the square over to its other side. When you perform a rotation followed by a reflection, the corresponding operation on the right becomes 0 plus 1 equals 1, or blue plus red equals red. What this is really telling us is that an orientation-preserving operation followed by an orientation-flipping operation always results in an orientation-flipping operation. Blue followed by red indeed gives red. We can even interpret this in terms of addition modulo 2. Think of the numbers 0 and 1 as counting how many times we have flipped the square. We count this modulo 2 because there are only two sides. So the morphism maps each symmetry to its orientation, and each relation on the left becomes a correct statement about the orientation of the square. That's the essence of a morphism. That's what I mean when I say that a morphism preserves all relationships. And now for an even bigger mystery. We originally discovered the concept of orientation by looking at the subgroups and cosets of the group. In other words, the concept of orientation came from the internal structure of the group. But this time, we didn't talk about cosets at all. We just mapped the symmetries of the square to a totally different group. So it seems that there is an interesting connection between morphisms and subgroups. We can discover concepts like orientation in two completely different but related ways. This is worth exploring in a bit more detail. This part of the video only applies to groups, no longer to monoids. We need the notion of subgroups and cosets here, and those only exist when we have inverses. Here is the addition table modulo 12 again. We start from one of its subgroups with its cosets. We discovered this nice block structure in the Cayley table earlier. We zoomed out, forgetting the contents of the blocks. The resulting structure is a new Cayley table, in this case, the addition table modulo 4. This is what we called the quotient group. Now let me put the quotient group next to the original, so that I can map each element to its coset on the other side. What we have here is a function that maps from one group, addition modulo 12, to another group, addition modulo 4. And due to the strict block structure, this mapping actually satisfies the definition of a homomorphism. Here, let's do a specific example. Let's add 10 plus 9. We can do this on the left, and the result would be 7. Then we map 7 over to the other side, and we end up in the block labeled 3. Remember that on the right we are doing addition modulo 4, and 7 indeed has a remainder of 3 when you divide it by 4. Now let's do the same operation the other way. We first map our inputs from left to right. 10 gets mapped to 2, and 9 gets mapped to 1. Again, you can see this as the remainders when dividing by 4. And what do you know? When we add 2 and 1 on the right, we get 3. Exactly the same answer as before. You could verify some more examples if you like. Or, if you feel more confident, you could try to prove, or at least convince yourself, why this mapping must be a homomorphism. It can't be an isomorphism because the quotient group contains fewer elements than the original. I now have to draw your attention to an important detail. All of the members of the subgroup on the left are mapped to 0, which is the neutral element of the quotient group on the right. This is not a coincidence. In the quotient group, the original subgroup always plays the role of the neutral element. Store this detail in the back of your mind, because we will need it in a minute. Okay, so every subgroup automatically leads to a homomorphism. What might be more surprising is that the converse is also true. Every homomorphism, between any two groups you can imagine, always gives us a nice, well-behaved subgroup. Here's an example. On the left we have our old friends again, the symmetries of the square. On the right we have a small group of 4 elements. I don't want to focus too much on the details of this second group, so I just represent each element with an abstract color. Purple is the neutral element. You can convince yourself that this is indeed a group by checking all the properties. Next, we map each element on the left to an element on the right. Of course, I could pick any mapping I want, but here I want to make sure that it's a homomorphism. I just do this exactly the same as before. I map the neutral element to the neutral element, and then I make choices for the two generators. Everything else automatically falls into place. You can do a few checks of the homomorphism property if you want. Now look at all the elements on the left that get mapped to the neutral purple color. This is called the kernel of the morphism. The kernel is defined as the subset of elements that are mapped to the neutral element on the other side. Surprise, surprise! This kernel is a subgroup. I'm giving only one example here, but it works in general. The kernel of a homomorphism is always a subgroup. Better yet, it always has well-behaved cosets, which give us a block structure. So, whenever someone gives you a homomorphism between any two groups, you just list all the elements that are mapped to the neutral element, and they always form a subgroup with a nice block structure. This is another trick that we can use for discovering new subgroups. Remember a few minutes ago when we looked at the homomorphism between a group and its quotient group. I mentioned that the subgroup on the left played the role of the neutral element on the right. So we basically started from a kernel and then found its homomorphism. This time we've gone in the opposite direction. Starting from a homomorphism, we discover that its kernel is a subgroup. So it seems that subgroups and homomorphisms are tightly connected to each other. When you think about it, this connection is actually really weird and unexpected. I mean, subgroups and cosets live inside of the group. By contrast, morphisms map to other structures outside of the group. Apparently, simply by looking at those external mappings, we can learn something about the internal structure. That's the kind of connection that typically makes mathematicians drool, because, once more, it gives them an opportunity to transfer their knowledge from one world to another. You have to admit that exposing the internals of an object simply by looking at it from the outside is a cool trick. I mean, imagine how awkward it would be if your outward behavior would completely betray all of your internal thoughts and feelings. And yet, that's what happens here with groups. Again, this is the kind of stuff that is studied in category theory, which is even more abstract than group theory. You could say that category theory only looks at the morphisms between groups. It completely ignores their elements, because we don't really need them. A famous theorem in category theory proves that everything you want to know about a group can be learned exclusively from the morphisms it has to other groups. You shall know a group by the company it keeps. We are getting close to the end of the series. After groups, where can we go next? One thing we can do is inject a second binary operation. Instead of only one operation like addition, we now have two, often referred to as addition and multiplication. The integers are a good example. They are already a group under addition. Even better, they are an abelian group, because addition is commutative. This is not a requirement for groups in general, but it is a requirement for rings. The addition operation must commute. Then we have multiplication. It's associative and it has a neutral element, the number 1. Unlike addition, multiplication does not turn the integers into a group, because there are no inverses. The inverse of 7 is 1 over 7, which is not an integer. So, under multiplication, Z is not a group but merely a monoid. That's good enough as far as rings are concerned. So, a ring is a set of elements with two binary operations. One of them must satisfy all the properties of an abelian group. The other must satisfy only the requirements of a monoid. But there is one additional rule. We want the two operations to be connected to each other somehow. Specifically, multiplication must distribute over addition. That completes the list of requirements for a ring. Note that, unlike addition, multiplication isn't required to be commutative. This means that n by n matrices can be turned into a ring. Matrix multiplication is not commutative, but that's fine. We don't need that for a ring. What are rings good for? Well, they have a whole host of applications. Think of any area of algebra where you really need two different operations. Polynomials, for example. They are a sum of several terms, and each of those terms is a product of several factors. So you need both addition and multiplication. That's why polynomials cannot be studied in groups, only in rings. Another very common application is divisibility. When you divide one number by another, you write out the relation like this. The large number is a product plus the remainder. Again, we can only express this when we have both addition and multiplication available to us. The power of rings becomes apparent when these two applications are combined. The study of the divisibility of polynomials has many applications in encryption. We're not going to spend any time on this topic. Instead, here's a cute little fact about rings. They have two different neutral elements. The neutral element for integer addition is the number 0. The one for multiplication is the number 1. And here's something curious. Under multiplication, the number 0 behaves like a black hole. It collapses everything else into itself. It is sometimes called the absorbing element for multiplication. It's easy to show that this is always the case. The neutral element for addition is always the absorbing element for multiplication, for any ring at all. Here's a short proof, just to give you a flavor of the kinds of algebraic proofs that you can expect in the theory of rings. Start from an expression of the form x plus 0 times y. After we apply distributivity, we get an expression with two terms. But we could also start by applying the definition of 0 as the neutral element for addition. This makes the 0 disappear in the original expression, leading to a result with only a single term. These two results have to be equal to each other, no matter which values for x and y we pick. So the second term, 0 times y, must disappear for any value of y. That's why 0 must have the property that whatever you multiply it with, the result must be 0. QED. Because this proof only makes use of the abstract definition of a ring, we now know that this result will be true in any ring we can ever construct. So the 0 matrix will be an absorbing element in the ring of matrices. The 0 polynomial absorbs all other polynomials, and so on. Just a single abstract proof gives us countless concrete ones for free. We now add two more requirements to our list. First, we demand that each element other than 0 must have an inverse for multiplication. In other words, we want to be able to divide elements, not just multiply them. The reason we exclude 0 is because we know that it absorbs everything, so you'll never be able to divide by it anyway. Finally, we want multiplication to be commutative. This makes the list of requirements nice and balanced. Any set of elements with two binary operations that satisfy all these requirements is called a field. The integers are not a field because there are no multiplicative inverses. Remember in an earlier video that we introduced the rational numbers so that division would always work. That makes the rationals a field. The reals and the complex numbers are also fields. There are even finite fields with only a finite number of elements. We won't go into any of these topics in the near future though. I really want to move on. Can we go even further than fields? We could, of course, add even more requirements to the list, but that would only make it more difficult to find a system that meets all of them. Or we could inject a third binary operation, or perhaps a unary one, just for fun. Instead, what we will do is introduce a complete new set of elements. So we start from a field, such as the real numbers, which we now call scalars. Next to it, we put a second set of elements that we will call vectors. We already have the two binary operations on scalars, addition and multiplication. On top of that, we introduce two new binary operations. One is the addition of vectors, which turns them into an abelian group. The second is a multiplication across the two sets of elements. When you multiply a scalar with a vector, this has the effect of scaling the vector. That's where the name scalars comes from. So a vector space has two types of objects and four binary operations. Just look at the complete set of requirements on the screen. How many there are. And yet, vector spaces are easy to come by. Earlier, we discovered many interesting new concepts that magically appeared out of the simple rules for groups. This time, exclusively from the abstract definition you see on the screen, we will be able to extract a whole new world of crucial concepts such as linear combinations, dimensions, eigenvectors, inner products, wedge products, geometric products, cross products, dual vectors, matrices, tensors, and much more. That's what the rest of our journey through algebra will be all about. Whenever we introduce a new kind of structure, it's always useful to find functions or mappings that preserve that structure. For monoids and groups, the structure consists of a binary operation with all its properties: associativity, neutral element, inverses. The mappings that preserve this structure are homomorphisms. They preserve the neutral element and the inverses and all the rest. For vector spaces, the structure is given by addition and scaling. Those are the only things you can do with vectors. So, we're going to look for mappings that preserve addition and scaling. These are known as linear transformations, and they are represented by matrices. Linear transformations will play the role in linear algebra that morphisms play in group theory. There are definitely many topics in group theory that we haven't talked about, such as group actions, the isomorphism theorems, automorphism groups, and much more. I've only given you the basics here. Also, I'm not going to cover rings or fields in any more detail either, at least not anytime soon. For those of you who are interested in doing more research, I have left some useful links in the description, as always. They include a detailed but very accessible series on groups, rings, and fields, and a free PDF that you can download with many great examples. I obviously appreciate your kind comments and your thumbs up for this video. Don't forget to subscribe if you haven't done so yet. If you like the channel and you want to make sure that we can keep making new videos, please support our work financially on Patreon. The link is in the description below this video. Thanks, and see you later.